In this lecture, you'll learn how to configure BGP in a service provider environment. And we'll use an example scenario that we're going to walk through. So you can see the topology here. We've got AS65001 on the left, AS65002 in the middle, and AS65003 on the right. And in the scenario, we are the service provider with AS65002 in the middle. We already have our IGP configured. We're using OSPF. And we've got OSPF running between R1 and R2. Also on R1, we've got OSPF route for the traffic at R3. In the example, R3 is one of our customers, and they've got the range of public IP addresses 203.0.113.72/29. You can see that up at the top at R3. So what we need to do is we want to have connectivity between all of those public IP addresses everywhere. So AS65001, that has already been taken care of by that service provider, and AS65003 has already been taken care of by that other service provider. We need to do all the configuration for AS65002. So we're going to configure BGP between our two routers, R1 and R2, and we're going to also configure BGP from R1 to R4 and R2 to R5. When you're configuring BGP internally between your own routers, it's iBGP for internal BGP. When you configure BGP to another AS, that's eBGP, external BGP. There are some different rules for how iBGP and eBGP behave, but they're both part of the same BGP routing process, and routes are shared between both iBGP and eBGP neighbors. The differences between iBGP and eBGP are not important here. If you go on to do CCNA service provider or take BGP at the CCNP level, you'll learn about them then. Okay, first thing to do is the neighbor command. And peering between routers works differently for BGP than it does for IGPs. BGP routers within an AS are often not directly physically connected. They can be multiple hops away from each other. So link local multicast to low messages cannot be used to form adjacencies. Link local multicast means it doesn't get passed on out another interface, so the two routers have to be directly connected for link local multicast to lows to work. BGP, they're often not directly connected, so that isn't going to work. You have to manually specify the BGP neighbors. You use a neighbor statement and you specify the IP address of the other router that you want this router to peer with. Targeted TCP sessions using TCP port 179 are used to establish the peering and also to exchange routes once the peering has been done. So you saw earlier in the section, we had the recap of how IGP works. You saw that we enabled the IGP on an interface. The router would then send out multicast, the link local hellos on that interface. And if there was another router directly connected that was using the same routing protocol, then they would form an adjacency. Or maybe not directly connected, maybe there's a switch in between, but they're on the same IP network. They're layer 2 adjacent to each other. In BGP, can't do that. They're often not directly connected. So what we do is you, the administrator, configures BGP and you specify the neighbor IP address. And obviously there must be a route to that neighbor IP address in this router's routing table so it knows how to get there. The neighbor relationship is set up using a unicast TCP session on port 179. So you can see in the example here, we've got R1 with loopback IP address 172.16.0.1, and we've got R3 with IP address 172.16.0.2, and there's R2 in between the middle of them. So we configure R1, we say that we want to form a BGP peering with 172.16.0.2. And then R1 will send that out as TCP unicast traffic. It says I'm 172.16.0.1. It sends that to the destination of 172.16.0.2, and it says that it wants to form a BGP relationship with it. R3 will reply within that TCP session, and it will agree to set up the BGP peer relationship if it has a matching neighbor statement for R1. When that is done, the routers will then exchange routes that are advertised in BGP as configured by you, the administrator. So our IBGP neighbors, they can be multiple physical hops apart and or have multiple redundant paths to reach each other. If the IP address of a physical interface is used for the BGP session, if that physical interface goes down, so will the BGP session, even though there's an alternative path to the router. If that doesn't make sense yet, you'll see it in the diagram on the next slide. Loopback addresses, which are advertised in the IGP, are typically used as the address in the neighbor statement because of this. This way, BGP peers can continue to reach each other even if a physical interface goes down. So let me show you what that means. You see in the diagram down at the bottom here, we've got R1 and R2, and we're going to form a BGP relationship between those two routers. And there's redundant links. There's two links connecting the two routers. We've got the 10.0.0/30 network on top, and the 10.0.0.4/30 on the bottom. So from R1, when we configure the neighbor statement pointing at R2, we could say we want to peer with 10.0.0.2 along the top path. But if we do that and that link goes down, then the BGP relationship is going to go down as well, even though we could have got to it along the bottom path at 10.0.0.6. And also, if we point at 10.0.0.6, we've got the same problem. If that path goes down, BGP goes down, even though we can get to the router along the top path. So what we do is we configure a loopback interface on both routers. We've got 172.16.0.1 on R1, 172.16.0.2 on R2, and we advertise those in our IGP. So R1 learns that it can get to 172.16.0.2 through 10.0.0.2 or through 10.0.0.4. And that way it will load balance traffic going to 172.16.0.2. If either one of the links goes down, it can still get there. So it makes it more stable and reliable, gives us redundancy. So that's what we're going to do to actually configure this. On R1, we say router BGP 65002. So this is the top level command you use to enable BGP. It's router BGP and then your autonomous system number. Then we configure the neighbor. The command for that is neighbor 172.16.0.2 remote AS 65002. This is an IBGP relationship. Both of the routers are ours in our AS, so it's the same AS number here, 65002. So we do that on R1 pointing to R2, and we do a matching statement on R2 pointing back towards R1. Okay, next thing. BGP has a security mechanism where it will only peer with another router if it has a matching neighbor statement for that peer. And the source address of packets received from the neighbor must match the exact IP address in the neighbor statement. Again, you're going to see what this means explained better with a diagram on the next slide. When a router sends packets from itself, it uses the IP address of the exit interface as the source address by default. This is not just for BGP, this is for all traffic. Like if you send a ping from the command line on the router, the source address will be the address of the interface that the packet goes out of. The router's, it's a router, so it's going to have multiple interfaces, multiple IP addresses on there. Whenever the router sends traffic from itself, it uses the source address of the interface it went out of. And this is going to cause BGP peering to fail between loopback addresses if we don't do something about it. So let's have a look and see what this means. So you see we've got R1 and we've got R2. On R1, we point it at the neighbor of 172.16.0.2. On R2, we've got a neighbor statement for 172.16.0.1. When R1 sends the BGP packet out to R2, it's either going to go along the top path or along the bottom path. If it goes along the top path, it goes out interface fast 1/0, which has got IP address 10.0.0.1. So that packet will be sent with a source address of 10.0.0.1. When it comes into R2, it looks to see, okay, this router is trying to form a BGP relationship with me. Do I have a matching neighbor? Do I have a neighbor for 10.0.0.1? No, I don't. My neighbor is 172.16.0.1, so BGP will not come up. R2 is not smart enough to realize it's the same router just using a different IP address. The IP address has to match exactly. So what we have to do is we have to tell R1 and R2, when you send that BGP traffic to each other, use your loopback address rather than the address that's on the exit interface. So if we don't make any changes, BGP is not going to come up. We can verify that with the show IP BGP Summary command, and you can see here that on R2, the neighbor 172.16.0.1 we've configured has not come up. We can see there's been no messages sent or received, and it's never been up or down. The way we fix this is we put the same commands in under BGP. So we've got the same neighbor statement 172.16.0.2 and remote AS 65002. And then we put in an additional command to specify the source IP address that we want to use. So we say neighbor on R1, 172.16.0.2, update source loopback 0. That means whenever you send BGP traffic to that other router, don't use the address of the exit interface, use the address which is on loopback 0, which is 172.16.0.1, which does match the neighbor statement over on R2, so BGP is going to come up now. So we need to do the same configuration on both R1 and on R2. And BGP will come up now. Again, we can verify it with the show IP BGP Summary command. And now we can see on R2 that we've got the neighbor 172.16.0.1. We can see that there are being messages sent and received, and it's been up for nearly a minute. So that is all good now. Now, notice this is a little bit different than with our IGPs. When we configure OSPF, normally the first thing we'll do is a show IP OSPF neighbor. For EIGRP, we'll do a show IP EIGRP neighbor, and that will show us a short summary of the neighbors and whether they're up or not. But in BGP, we don't use show IP BGP neighbor to get a summary. It's a different command. We use show IP BGP summary, and that will show us a short summary of all the neighbors, whether they're up or not. We can actually use the show IP BGP neighbors command as well, but it doesn't just give us a short summary, it gives us really long verbose output. So you can use this command if you want to get more detailed information, but if you just want that summary information, it's show IP BGP summary. You'll notice in here when we do the show IP BGP neighbors command, this is on R2, and we can see that the neighbor 172.16.0.1, which is over at R1, the BGP state is currently established. That is good. If you see BGP state active, it sounds good, but it's not. It's bad. It means that it's actively trying to establish peering and it's failing. So active is bad, established is good. Okay, so we've got our iBGP neighbors configured. The next thing to do is configure our eBGP neighbors. So on R1, we say router BGP 65002, again under the same BGP process. Neighbor 203.0.113.65, the IP address over on R4, and we say remote AS 65001. The router can see that this is a different AS than our AS, so it knows that it's an eBGP neighbor. And we do the same thing on R2. We configure a neighbor statement pointing to R5 on there. So we've got all of our BGP neighbors up and configured. Next thing that we need to do is specify the actual networks that we want to advertise in BGP. But we've been going for quite a while in this lecture. Must be time for a break. So we'll cover advertising networks in BGP in the next lecture.